So welcome you all in this lecture series of optical communications, and in this lecture we are going to deal with the concept of total internal reflections, then acceptance angle, numerical aperture, what actually the meaning of these things, and apart from this we will see what is the meaning of askew rays. So this is the law of reflection and refractions that we all learn in our basic elementary education level, that is the 11th and 10th. So whenever a ray of light is incident, is moving from one medium to another medium, and if we say that the refractive index of a first medium is greater than the refractive index of the second medium, or the refractive index of a first medium is less than the refractive index of the second medium, then what is happening? The light ray, whenever they are falling at the point of interface of a two different medium, so we can easily see that there are two different mediums, N1 having a materials having a different refractive index. First is your N1, another one is your N2. So the boundary of these two medium is separate. This is a material boundary. Now there is a line, that is an imaginary line drawn normal, that is a perpendicular to the interface or perpendicular to the intersection of a two different medium. And whenever a incident light is incident at a point which is separating two different medium, then we will see that whatever the angle, incident angle made by a incident ray, this is a phi 1 is called as the incident angle, that is drawn between a incident ray as well as the normal in the first medium. So whatever the angle, this phi 1 is called as the incident angle. So when a ray is moving from one medium to the other medium, and if we are having this parameter that N1, that the refractive index of a medium first is greater than the refractive index of a second medium, in that case the refracted light will move away from the normal, because the refractive index of a second medium is less than the refractive index of the first medium. So as a result of that, it will move away from the normal. While the other case is that if the refractive index of a second medium is greater than the refractive index of the first medium, in that case whatever the light is incident moving from a first medium to the second medium, in that case it will move towards the normal. So if I am saying that it will move towards the normal, so that will be something like this. So it will be something like this. That means it is moving towards the normal. So this phi 1 is called the angle of incidence, as well as this phi 2 is called as the angle of a reflection, because it is the angle made between a refracted ray as well as a normal drawn perpendicular to the interface of two different medium. So this is a refracted ray, this is an incident ray, and this is a reflected ray. So if whatever the ray that you are incidenting at the point of intersection or the point of interface of two different medium, that ray bounces back to its original medium, then we say that the ray that bounces back to its original medium is called as the reflected ray. Whereas if a incident ray is moving from one medium to another medium and it is deflecting its directions, that is, it is moving away from its original direction, then we say that the ray is a refracted ray. So this is the case in if N2 is less than N1, and this is the case if N1 is greater than N2. That means your refracted ray will move away from the normal. So as per this, if it is a reflection, so as per the reflection law, the angle of incidence will be equal to the angle of a reflection. Now we have already seen this law called as the Snell's law. In this Snell's law, as per the Snell's law of refraction, it says that N1 into sine of the incident angle equals to the N2 into sine of the refracted angle. So that is the Snell's law. N1 sine phi 1 equals to the N2 sine phi 2. Right. So that is the basic for your reflection, refraction and Snell's law. Now after this we have to see the numerical aperture, and we have to understand how you can derive the actual expression of the numerical aperture. After that we have to see what is the concept of your total internal reflection. Now if we can see this figure, the incident ray, the light which is moving inside the fiber, that means light which is striking the air and core interface at an angle theta 0, this is called as the acceptance angle. So any ray which is incidenting at a core and air interface at an angle greater than the acceptance angle, then that ray will not pass through a fiber. That ray, after intersecting, after meeting at the core and cladding interface, will move into the cladding. So if you want that your ray should travel along the fiber and reach at its destination, then you have to follow, or you have to incident the light at an angle which is less than the acceptance angle of the fiber. So if suppose I am incidenting my light at an angle which is less than the acceptance angle of the fiber, then it will, after crossing the medium, that first medium is your air, then we are having a core. The refractive index of a air is less than the refractive index of a core. So it is moving from a lesser denser medium to a denser medium. So obviously it will move away from the normal. It will move away from the normal. So after moving away from the normal, it is striking at the core cladding interface. So if you are meeting the condition of your acceptance angle, that means you are striking the light at the core and glass interface at an angle which is less than the acceptance angle of the fiber, in that case you are ensuring that it will follow the condition that your light is striking at the core clad interface at an angle which is greater than the critical angle. If this is your phi, if this is a phi and you are saying that your phi is greater than phi c, that means the critical angle, that incident angle is greater than the critical angle, then in that case that light will be reflected totally to its original medium. That is your total internal reflection. So if suppose that we have already seen the Snell's law as N1 sine phi 1 equals to N2 sine phi 2. That N1 and N2 are the refractive index of the two materials, and this phi 1 is the incident angle and phi 2 is the refracted angle. So if for the critical angle, what is happening? This is your N0. Here basically you are concentrating on this region. So it is sine phi 1 equals to n2 upon n1 sine phi 2. So we can say that if your incident angle is the critical angle, that means if phi equals to phi c, then that is n2 upon n1 into sine 90 degree, right? So that means it is equal to n2 upon n1. Your critical angle sine phi c equals to n2 upon n1. So in this way, we can calculate the critical angle of an optical fiber. So if your ray is striking at the core, this is your core and this is your clad, and this is the interface of a core and clad. If your angle of incident, that is a phi, is greater than the phi c, then in that case your light will be totally internally reflected. So that is the condition for your critical angles. We can also see in this case also. So in this case, because this is the very basic form, n1 sine phi 1 equals to n2 sine phi 2. This is the Snell's law that we have already discussed. So as per that, we can easily say that sine phi c equals to n2 upon n1 sine 90 degree. So finally your phi c equals to sine inverse refractive index of a rarer medium and the refractive index of the denser medium. So that is the expression for your critical angle of the optical fiber, and your ray have to strike at an angle greater than the critical angle if you want that your incident ray should be totally internally reflected. So that is the condition of a critical angle. And if you are striking the ray at an angle equals to the, if you are striking the ray at an angle equals to the critical angle, then in that case how your ray will be refracted. So in that case, it will be the angle of refraction will be exactly the 90 degree. So this is your angle of refraction. But the case, if you are considering a case in which your incident angle phi 1 greater than the critical angle, in that case your ray will be totally internally reflected. So that is the concept of a total internal refraction in the case of your optical fiber. Now, so if you are inserting your light at an angle less than the acceptance angle of the fiber, in that case you are ensuring the criteria that whatever the after refraction, whatever the light traveling after crossing the interface of air and core, it will strike the interface of core and cladding at an angle greater than the critical angle, in order to ensure that to follow the phenomena of total internal reflection. And it is with the help of this phenomena of total internal reflection, light will follow a zigzag path and it will emit at the extreme end. So this is the concept of a total internal reflection. And these two angles That is, first is called as your critical angle, and the another is called as your acceptance angle. This critical angle is the minimum angle, it is the minimum angle at which your ray or your light ray have to strike at the core clad interface so that your ray, your angle of refraction is 90 degree. It is the minimum angle that is required for a ray to be refracted at a 90 degree at the boundary of a core and clad. And if your incident ray is greater than this critical angle, then in that case it will move inside the, bounce back into the same region, and it will travel along the core of the optical fiber. Whereas acceptance angle is the maximum angle of an external ray. This is your external ray. Acceptance angle is the maximum angle of external ray, the angle, maximum angle at which your external ray should strike the air, and core region. It should maximum angle at which it should strike the air and core region so that your ray is transmitted inside the optical fiber. How your ray will be transmitted inside the optical fiber? Because this is the criteria. That means if you are maintaining an angle of an external ray incident angle at an angle less than the acceptance angle, then it is ensuring that it is going to strike the core and clad interface at an angle greater than the critical angle, so that it should be totally internally reflected. And with this phenomena of a total internal reflection, your optical ray will travel along the core of the optical fiber. Now, apart from this, there is one more thing, that is the two ray, that is your meridional ray and a skew ray. So, meridional ray is a light ray. If a light ray is striking at the center of a optical fiber, if a light ray is striking at the center of a optical fiber, that means if a light ray is striking at the axis of a core, this is your axis of a core, then it will follow a total internal reflection and it will follow a zigzag path like in this way. It will follow a path like this, right? So, this is the meridional ray. That means a ray which is striking at the center of optical fiber, and the center of optical fiber is the center of the core. If it is striking at the center, at a point which is exactly at the center of the core, then it will follow a zigzag path while traveling along the optical fiber. So, this is the meridional ray. Now, the next thing. So, we have already discussed the meridional ray, because we are seeing that the ray is striking at a point which is exactly at the center of the core, that is center of the optical fiber. So, if it is striking at the center of our optical fiber and that too maintaining the acceptance angle of our optical fiber, then it will ensure the total internal reflection phenomena and it will travel along the fiber by following a path of a zigzag way, right? So, this is your meridional ray. So, apart from a meridional ray, you have one more ray which is called as the skew ray. So this is your skew ray transmission path. If your light ray is striking at a point apart from the center of the optical fiber, if it is striking at a point apart from the center of the optical fiber, then it going to follow a helical path. It is going to follow a helical path. It's not going to travel along the axis of optical fiber, but it will going to follow the helical path. This figure is depicting the concept of your skew ray. So we can easily see that whatever the ray that is striking apart from the center of the optical fiber, that this one, it is striking, this is your skew ray, which is striking not at the center of the optical fiber, but point apart from the center of the optical fiber. So it will follow a multiple total internal reflection, and it will move in a helical path. There will be multiple total internal reflection like this way, and it will follow a helical path, and it will move out of the optical fiber. So this light ray, if it is a skew ray, so whatever the light ray that is emerging out of the optical fiber, it's going to depend upon the whatever the multiple total internal reflections that is taking inside the optical fiber. Whereas in the case of your meridional ray, which is striking at the center of the fiber axis or at the center of a core, once it is striking at the center of a core, and that too following the acceptance angle, then it will travel a path which is your zigzag way, right? It will travel a zigzag way. So the two ray, that is a meridional and a skew ray. Meridional ray is a ray which is striking exactly at the center point of the core, and it will travel along the fiber by following a zigzag path. And the light, if you are using a meridional ray, so whatever the light that is available at the output of an optical fiber, going to totally depend upon the acceptance angle. All right, it will totally depend upon the acceptance angle. If you are inserting the incident light ray at an angle greater than the acceptance angle, definitely it's not going to follow a total internal reflection phenomena. It will move inside the clat region, right? So in the case of skew ray, we saw that the output available at the output of the optical fibers going to totally depend upon the multiple number of a total internal reflection taking place inside the optical fiber. Whereas in the case of meridional ray, the light that is available at the output of a optical fiber going to depend only upon the angle of the incident ray, the ray which is incident at the air and core interface. So this is the concept of your meridional and a skew ray. Now, so this figure is clearly indicating the concept of acceptance angle. If a ray which is within the acceptance angle, how it going to travel, and if a ray which is incident at the air and core interface is beyond the or greater the angle of acceptance angle, then how it's going to travel inside the optical fiber. So this is the acceptance angle of the optical fiber, that is alpha. Right, this is alpha. This is the acceptance angle of the optical fiber. So in this case, this is the maximum angle at which an external ray have to strike the core and a glass interface in order to travel along the fiber axis. How it going to travel along the fiber axis? Definitely, if it is following a total internal reflection, then it's going to travel along the fiber axis. So we are saying that is the maximum angle at which an external ray has to be incident at the core and the glass interface so that it will travel through the optical fiber. Now, if a ray, we are considering a ray that is B and O. So we are incidenting a red ray with an angle which is less than the alpha, that is the acceptance angle. So if it is a less than the acceptance angle, we are ensuring that it will strike the core and clad interface at an angle greater than the critical angle. So this is the condition. If you are striking your light at an angle within the acceptance angle, then you are ensuring that it's going to that your ray after refraction from your air and core interface, it is going to strike the core and clad interface at an angle greater than the total internal reflection. While on the other case, if you are considering a ray that is A and O, that is AO, if you are considering this ray which is beyond the acceptance angle of an optical fiber, so this ray, if it is beyond the acceptance angle of an optical fiber, then after striking the air and after striking the core and clad interface, instead of following the total internal reflection phenomena, it will move into the clad region, because you have not ensured the criteria for your ray to follow, for the criteria for a ray to follow the total internal reflection at the core and clad interface. That is, you have gone beyond the range of an angle at which you have to strike the ray at the air and core interface. So remember that your acceptance angle is the maximum angle at which you can incident an external ray so that it can be traveled through the fiber, right? Whereas a critical angle is the minimum angle, right? It is the minimum angle that which you have to follow, and your ray should strike the core and clad interface at an angle greater than this minimum angle. This minimum angle is called critical angle. Your ray should ensure this condition of or it should be greater than the angle of the angle which is called as the critical angle in order to follow the total internal reflection. So remember that critical angle is the minimum angle, whereas acceptance angle is the maximum angle. So this is the condition. If it is a within acceptance angle, it will travel along the fiber, and if it is beyond the acceptance angle, it will move inside the clad, and it's not going to be received at the receiver, and it's not going to travel along the axis because it is moving inside the clad, and after some distance it will be completely degraded. Now in this case, we have to understand the concept of a total or concept of a numerical aperture. Numerical aperture is defined as the light gathering capability of a fiber, right? It is light gathering capability of a fiber. Numerical aperture is called as the light gathering capability of the fiber. So higher the numerical aperture, higher the amount of light will be coupled through the fiber. So now we have to derive a expression for the numerical aperture. We have to achieve a condition that is sin theta A equals to numerical aperture equals to under root of n1 square minus of n2 square. So it is a very simple derivation. In this case, as you are concentrating upon the numerical aperture, so you have to concentrate on the air and core interface. That means this region, you have to concentrate on this region. So if you are concentrating on this region, you have to follow, you will apply a Snell's law, which says that n0 sin alpha equals to n1 sin theta. Now this theta can be expressed at pi by 2 minus phi c. So we can again rewrite this as n0 is the air, so this refractive index will be 1. So sine alpha, that is equal to n1 sine of pi by 2 minus phi c. So this will become n1 cos phi c, which can be rewritten as n1 under root 1 minus sine phi c square, right? Phi c or theta c. So we have already write the phi c, so let us consider this as phi c. So you know that the critical angle sine phi c is n2 upon n1 whole square, right? So we can rewrite this as sine alpha equals to under root of n1 square minus n2 square, which is equal to the numerical aperture. And this sine of alpha is also called as, this alpha is also called as the acceptance angle theta a. So we can write it as sine of theta, sine of theta a equals to the numerical aperture equals to the under root of n1 square minus of n2 square. So this is the expression that is showing your numerical aperture and the acceptance angle of a fiber. So we can see that numerical aperture is depending only upon the refractive index, not on the radius of the core, and your theta, that is theta a, which is your acceptance angle, is equal to the under root of n1 square minus n2 square. So this is the expression for numerical aperture. And once again, let me tell you that numerical aperture is the light gathering capability of the fiber. So higher the numerical aperture, higher will be the light that will be coupled inside the optical fiber. So in our next class, we are going to continue from here. So we are going to discuss some new interesting topic in the unit 1. So let's see in our next module of this lecture. Thank you all.